The broadcast is now starting. All attendees are in listen-only mode.
Welcome to everybody. My name is Murray Frank. I'm with Constructive Home Solutions. I'll be moderating today. I have the great pleasure of introducing Graham Finch. I'm just going to wait for the countdown to reach a little bit higher. We're about 22. We're expecting closer to 50 people here. So if you have a last minute cup of tea or something you want to grab, now would be your last chance. All right, I think we'll just jump right in and get going. I personally am very excited to hear what Graham has to say. I debriefed with him a little bit. We've been involved in some projects off and on at various levels over the last few years, and he's going to be speaking on a subject of how mass timber buildings will disrupt the facade and window industry. And this is a little bit near and dear to my heart. We're working on a project in single family residence right now. We're building it at, we're calling it Step 5 Plus or Step 5 Beyond. It is fascinating, the things that we've learned in this process, and fascinating, frustrating in some regards, fascinating, eye-opening, and pleasantly surprising in some regards. So I'm very excited to present to the group here, Graham Finch, who's a principal with RDH Building Science. He leads their brigade over on the island. He cut his teeth in the Lower Mainland office. Graham and I go quite a ways back from the time when he was still somewhat influenceable. Hopefully I had a positive influence on all of that. I think you'll find that Graham's knowledge is quite deep. He's probably going to be presenting at a level that's 1/10 of the way down into what he's truly thinking. So we're going to try and nudge things out at the end with some questions. There is a chat room on there. Zena has just entered in a little note in there. If you just want to have a comment as you go along, I'd be very interested, and I'll follow along with those. There's also an opportunity to add questions if you want. And if we can stack those all up, what I'll do is give Graham about 5 or 6 or 7 minutes at the end here to address those. But because I'm sure this is going to be rich with content, you don't want to hear from me. So without any more delays, Graham, I pass it over to you, and thank you so much for being with us here today.
Thanks, Murray. Can you hear me there? Just make sure we're sound check.
I can hear you just fine. I don't see anybody else complaining yet, so it sounds good.
Good. All right. Thanks, Murray. Thanks, Zena, and thanks, FenBC, for this opportunity to share some of the current research and projects that we're working on. Some of the observations I'm seeing in the industry that see a lot of opportunity. See on current projects as frustration because we're actually lacking suppliers to be able to help in a lot of respects. So I'm a bit of a call to arms here and an opportunity for the industry at large actually to meet this need that's growing and only accelerating. So with that, I'll jump right into the presentation here today. So today I'm going to be talking mainly about mid and high-rise building enclosures because this is where a lot of this work is developing, but it's filtering down and it definitely applies into smaller structures as well. And there's an opportunity for all buildings here. And it's something we're seeing coming out of this sector that will make its way throughout the rest of the industry. So when we look at high-rise building enclosures today, traditionally they're built out of concrete, steel, glass. And then Vancouver, Lower Mainland, and a lot of newer cities, a lot of curtain wall and window wall, a large fenestration component, right? And that makes up most of our cities and our high-rise facades. When we look at high-rise facade materials and systems, we have a mix of site-built and prefabricated. And what we're seeing more and more, especially with taller buildings in urban areas, there's more and more prefabrication of components. And curtain wall and window wall are great examples of existing prefabricated facade systems, as is precast and steel stud systems. But we're seeing this shift from things being built on site in multiple layers to prefabrication. And there's a number of drivers that are currently accelerating that. Now, it's important to realize that prefabrication is not new. It's been around for decades now, and the industry is still growing, but it also has a lot of good established practices. You got things like precast concrete systems, curtain wall, window wall, as I mentioned, steel framed wall panels, and there are suppliers of these systems all over North America, and many in British Columbia as well. But that's the need for these systems is starting to change, and also both because of energy, but also because of more buildings requiring prefabrication at a higher level of performance. So today I'm going to talk about where we're going next. We're already starting to see it. There's many projects, R&D, competitions underway that are bringing it to the next level, which is really exciting in British Columbia right now, but also beyond in Canada and the US. And what's leading to this is it's really a confluence of drivers. We've got energy codes, we've got mass timber buildings, which we'll talk about here. We've got carbon discussion of carbon efficiency and carbon in buildings. And so this whole confluence is leading to this, what I like to call next generation facade systems, building off where are we going next. So when we look at these drivers and where we're going and why we're getting pushed into prefabrication, for example, is first, there's sort of three main things that have been driving this for some time. The first is physical, the height of the building and the accessibility of the sites, right? When you look at taller buildings in our cities, especially as two sides are over adjacent buildings, you just can't put scaffolding up around some of these buildings, so you have to prefabricate and fly in the facade systems with those. We just don't have accessibility. And also the taller and taller you go, it's just not safe to put up scaffolding up really tall buildings or even lifts. And relying on building piecemeal with swing stages, that's really becoming a challenge now. Practical. When you look at how fast our clients desire buildings to be built or need buildings to be built to be economical, you've got that aspect in there. We've got challenges with costs, and costs are always going up. But the big one lately is labor availability, right? Just in a lot of cities, places like San Francisco, for example, labor is so expensive or it's just not available. And so that's really driving up facade costs. And so labor and shifting that labor from the site into factories is actually one way to manage that availability and also address cost at all the same time. And then the third driver, it's becoming more complicated, and the complication is being driven by higher levels of energy efficiency requirements, air tightness, perfection in sealing, and also carbon is also driving that as well. And so what people are finding is it's also a lot easier to build a lot of these exterior insulated and more complicated wall and window systems on the ground instead of piecemeal on swing stage or on scaffolding. And so the physical, practical, and environmental reasons are pushing towards largely a growing market for prefabrication. If we pause for a bit too, at the energy efficiency impacts on the facade, that's another huge driver we're seeing, and also what's pushing, I think, pushing that sort of tipping point over the edge. You look at this building here. This is actually a mass timber building that's under design in Toronto. And there's two facades, you got all glass on the left, which looks very slick and interesting, and exposes the wood, versus the one on the right, which is a little more closed in, a little more thoughtful on the windows, and actually has some walls there with some thermal performance. And that building on the right, and the design on the right, that's the one that's going to meet the energy goals of this project. And the one on the left just can't meet it because of thermal performance and of those systems. So we're seeing a shift from that all glass to more thoughtful glass and higher performing walls. And so what we're seeing with energy efficiency requirements, whether it be step code, passive house, net zero, 100% window and curtain wall systems, which are great prefabricated systems, as the facade, have pretty mediocre opaque thermal performance. You're lucky to get, R5 for the spandrel areas, maybe you can get R10, but we need to get to like R30 or R40, and you just can't get there with current systems without a lot of change. And so that's the challenge. That's what we have. We have to step up to this challenge. And so how is the industry responding? Well, unfortunately, it's a shrinking window market as a percent of the enclosure area. So some might see this as a bad thing. And so we want to turn that frown upside down and look at the potential solutions to this as well. If we're reducing window area, how do we get that piece of the enclosure back? And so the new paradigm is higher R-value wall systems driving the design to meet your energy code for net zero passive house as 100% of the facade. So the wall is actually driving the facade instead of your glazing systems, with strategically or appropriately sized and installed windows and doors into those systems. So the wall rather than the window is driving the design. And the opportunity here is for manufacturing of actually higher value wall systems with pre-installed windows, installed like curtain or window wall, or curtain and window wall systems performing to the level that we need to here. And that's why we're starting to see that change. And so what the opportunity, especially for the fenestration industry, is you could think about, you actually could now do 100%. You looked in the past and your market of the enclosure area was shrinking, went from 50 to 40 to 30% of the enclosure area, and your projects were getting smaller and smaller. Think bigger. Now think 100%. I'm going to do 100%. I'm going to produce the walls and the windows together. And so it's these combined wall and window systems and prefabricated is where we see a lot of trends, and where also a lot of opportunities here. So as window suppliers, you either might be providing windows for these systems and installed in the factory, which is a lot nicer than installing on site, or as a window manufacturing company, you might be developing wall systems or wall panels, let's say, that go with your windows, so you can do everything yourself. And therefore, you went from 30% of the market to 100% of the market. And that's the opportunity. So why is this happening now, and how does mass timber fit into this? Well, we have it's a bit of a catalyst here. So we've got our physical constraints, as I mentioned, why we're seeing more and more prefabrication, the height, accessibility of sites, especially with taller wood buildings, that's going to be a constraint. And then practical, we need to build fast, and we'll talk about mass timber, how we need to build even faster with the facade than traditional concrete and steel buildings. And environmental goals. This is a big driver for higher energy performance, the right amount of insulation, sealing these things up, becoming airtight, and also the piece on carbon. And if you want the catalyst or the piece that pushes us over the edge, or that little molecule that comes in there and totally disrupts it, it's that mass timber. And this is where we're seeing a lot of this innovation come, and it's filtering down for other buildings. So we've developed systems for mass timber projects, and they're now being used on all other building types, and they work quite well. And why is mass timber that catalyst? So many people are familiar with Brock Commons and the story there. I like to use it as an example because it's a good case study to highlight it. But you can see here the mass timber structure, and in pretty much lockstep, 1 or 2 floors behind, you've got the facade system being installed. 2 days doing structure, 2 days doing enclosure, and you're getting 1 to 2, by the end of it, 2 floors of enclosure for every week, right? And so if you can build that fast, if you can go from more than a 1 week turnaround to less than a 1 week turnaround on your structure enclosure, that changes things. And the reason we're also seeing this with mass timber is you need to protect that structure with the enclosure as you go up for moisture reasons, which also tie into fire protection reasons as well. So to summarize, if we have high-rise buildings, we have a choice between site-built versus prefabricated facades, and we always have. And whether we site-build something or we prefabricate it, it's going to be market design and speed dependent, and also maybe just even experience what we've been doing. We're seeing already with passive house projects, it's shifting that pendulum towards prefabrication, and the reason being is we're adding more insulation and need better quality control and thermal bridging, insulation installation, air tightness. So we're seeing the desire for prefabrication pop up more and more with this. So if you have a high rise that is passive house, it's more likely to be prefabricated or need to be prefabricated instead of site built. If you add mass timber in there, it's very challenging to build a taller mass timber building without prefabrication. And if you don't consider it, you're potentially missing some opportunities. And if you do build a tall mass timber building without prefabrication, you're going to potentially run into moisture and construction challenges, and it likely is going to slow down the rest of the building. So, those three things together result in prefabrication. And so that's why we're, that sort of, passive house and mass timber, and we're seeing a number of projects like that right now, and they're all going prefabricated for facade systems. And then the last piece is if people and design teams are looking at carbon and the carbon equation very closely and trying to get every material in there assessed from a life cycle assessment, you'll find that actually introducing wood into your facade systems is another strategy in addition to that wood structure that you can reduce carbon even more. And then so what we're seeing here is something entirely new, and it's prefabricated wood-based facade systems that I'll talk about here and how that works and how that's safe and how we address fire structure and moisture and durability. But that's a growing piece of the puzzle here, and we're working on numerous projects that are pursuing this, and there's competitions now that are spurring the industry to develop these types of systems to meet this need. So just a quick discussion on carbon and why that's becoming apparent here and something to think about and talk about in our industry is, we have, when you look at carbon, and you look at greenhouse gas emissions and carbon equivalent, you have two pieces. You have operating carbon, right? So operating carbon is the carbon equivalent that's emitted as part of your operation and maintenance, right? And so the more energy efficient your building is, pushing it closer to net zero, step code, upper steps, passive house, the lower operating carbon you will have in your building. Okay, so energy efficiency is the first lever on carbon. Embodied carbon is also quite important, and embodied carbon is all the carbon that goes into the construction and then the life cycle of your building. And so it's the equivalent of the acquisition, the manufacturing, the transportation, and the installation of all the materials. And wood versus concrete is an example. Wood is significantly better, lower carbon material than concrete. And wood, when you look at wood as a material, actually stores or sequesters carbon. So you actually get negative numbers, which take away from other materials that are positives in some cases. And so there's always a big argument in the industry about wood versus concrete. And when you're talking carbon, wood tends to win that discussion. And so much so that the concrete industry is now, how do we sequester carbon in concrete, and how do we address the challenge with cement production, which is the big driver there. And so in British Columbia in particular, and other jurisdictions where your energy grid is electricity based, right? You're using hydroelectric or even nuclear or other, you have a clean grid. So if you have a low carbon grid, like in BC where we have a lot of hydroelectric, or Quebec, and you have energy efficient building standards like net zero and passive house, embodied carbon that's actually more than the operating carbon in these buildings now. And so that's why we're actually seeing, in particular BC on the West Coast, we have a clean grid, we have energy efficiency standards, and now when you look at that pie that's left at the end of the day, embodied carbon is the biggest piece, and that's what drives mass timber, or one of the drivers of mass timber. And so for mass timber buildings, it's about looking at the wood in there and looking at the carbon equation. How does the wood in that structure impact the carbon equation? And it's typically a positive, and that's why it's a positive benefit to the environment. And there's all sorts of statistics that you can pull together for how carbon is saved or is sequestered in mass timber buildings, as an example. So what we're going to talk about next is that driver towards mass timber based facades, but also just prefabricated higher thermal performance facades as a result. So it's driving two sort of parallels together, where we're more energy efficiency and then the option if we want for mass timber. So when we talk about mass timber buildings, typically, the industry talks about structures, right? We're talking about the components that go into that building. We're talking about the structural systems, and often, the building enclosure is, maybe in the third or fourth line or the last page and talked about, briefly. But the building enclosure plays, a very important role in protecting these buildings, of course, both in service and during construction. And also, it allows these buildings to be built, but also to perform in the way that they're intended, of course. The first thing is with these design and mass timber buildings is using wood where wood makes sense. That's like the fundamental. You don't put wood below grade. You typically elevate all the wood. The wood is used in, typically your floors and your columns and your beams. You can do cores out of wood as well. You just may need some more steel and connections in there. But typically, you're always going to have a mix of concrete, wood, and steel. And using it where it makes sense. Mid-rise, low-rise building, you might use wood cores. If you're going to a taller building, you might have core system, or you might have a braced frame. So there's all sorts of different structural systems that allow mass timber to go up to 30, 40, or even taller stories tall. But you're always going to have a mix of materials. So tall wood structures in all these buildings, it's important to realize that because they are prefabricated components themselves, they will be erected quickly. And so they're going to go together fast. That's the intent. But also at the same time, while they're going together, we need to protect them from moisture. Wood is sensitive to moisture, as we know, so we need to protect it. And so the enclosure and waterproofing elements play a big role in that. With wood structures, depending on the design, the lateral load system, they may be more flexible than steel or concrete. Not always, but they may be. And so that means you might see more interstory drift. So your curtain wall system, for example, might need to take an extra inch of interstory drift than maybe a concrete building. But that's something that, sort of project by project dependent. So something to be aware of. And you're going to see mixed connections. And then, for all the different materials that go in there. And then the other piece of this puzzle that we're seeing, and even in BC and Canada, is fire codes are going to dictate the protection of that wood during a construction or erection. And so the exposure of the wood needs to be protected during construction, but also when it's complete, you may need to encapsulate it, or you may need to rely on the wood itself for fire protection. So the first question always comes up is, well, how do I, are tall wood buildings safe, and how do we protect them from fire? And actually, when you look at the wood components used in mass timber buildings, you are talking big pieces of wood. And big pieces of wood, unlike sticks of light frame construction, are actually quite difficult to burn, but they also burn in a pretty predictable manner. It's like the analogy, it's pretty hard to light, a log on a fire. If someone told you to light a fire, you wouldn't just take a log and hold a match to it. You're going to break up that wood into little chunks, kindling, use small shavings and some paper in there maybe, and you're going to start a fire. And that, so, when you look at mass timber, it's that log analogy where it's actually very hard to start the fire there. But there are two ways to protect it, and it's very similar to, steel buildings, where you protect them with gypsum or other fire protection. So you can encapsulate. So the one measure is you encapsulate all the wood in fire protection, whether it be mineral wool type insulation, gypsum, other products. So you can encapsulate it, or you can use a char method where you design the structure so that in a fire, you get a fire rating out of that char. And then you have that, your members are typically oversized, so you can get out of the building in the case of a fire. And so that's typically the two approaches that are being taken. Code in BC is now allowing encapsulated up to 12 stories. And with time and as codes change, we'll see more and more adoption of char, and many buildings have been built with either approach as the strategy. Both work. When you look at facades, so putting mass timber in our facades, the first question is, well, how do I do that safely from a fire protection standpoint? Again, using similar techniques to the structure. We either encapsulate it with gypsum or other materials. On the inside, we'll typically use non-combustible claddings and insulation. On the outside, we'll do fire testing to make sure all this is safe as well. Or you may oversize your structural members so that you can get char as well. So you can either encapsulate or char your facade systems if you're using wood in there as well. And then there are different requirements for 1 or 2 hour ratings, whatever you need, depending if it's load bearing or not load bearing. When you look at building enclosures for tall wood, there are 2 things that we constantly fall back on in terms of design drivers. We have first a need for speed. We need to erect and seal the enclosure as fast as possible to protect that wood structure from moisture. And this is certainly apparent in coastal regions, but it's also important in other drier regions as well, just to get things sealed up as quickly as you can and not slow down construction. As a result, there's a preference for that prefabrication with minimal site prep. We don't want to be putting peel and stick over our slab edges if we can avoid it. And we want to be just, dropping in panels on the outside and be done within a day, a floor per day, if we can achieve something like that. Whatever we install too, we don't want, if it's raining out, which it will be a number of days of the year, this materials on both sides of that panel have to be accommodating of inclement weather. So when you look at the materials, you may not put the drywall on the inside, for example, and maybe the bad insulation, but everything that's installed here is designed so it can get wet and then dry back out. Durability, especially in the emerging industries, is extremely important. We need to use the right materials. We're building high rises here, not houses, so we have to step up the game. Typically on the selection of materials, window systems will be mid to high rise appropriate, higher MAPS ratings, performance grades. The durability, we need to carefully consider the movement we're going to see, whether in load bearing or hung applications. Energy efficiency is at the forefront, of course, so these are going to be thermally efficient. And then non-combustible, whether we use encapsulation or char, and then we test to make sure. So we build confidence that these are safe. When we look at high versus low rise structure considerations, tall buildings are quite repetitive. They're quite exposed to wind-driven rain on the floor slab. There's need for more speed with these to get up to the roof and seal it up. So these are ideal candidates for prefabrication. You'll tend to see that tall buildings will definitely lend themselves that way. It's actually more about getting your walls on rather than the roof, which can be quite small for weather protection, right? The roof up here isn't going to protect the walls, the indoors here if you don't have the wall panel on down here. A lot of water just goes inside and wind-driven rain and then just runs itself down. So we need to get the whole thing sealed in. When you look at low-rise structures, potentially, some designs might be less repetitive or you have less panels. And so when you have less repetition or less components, it may not be as advantageous to go to prefabrication, but it can be. We've seen a lot of the 3 to 4 to even 6-story mass timber buildings. They'll be built stick built from ground, slower of course, but in that case there's also greater focus on the roof, getting the roof on and sheltering this and its overhangs potentially than the walls. So it doesn't say you have to prefab, but it's definitely if you're going taller and if you're going more repetitive, it definitely lends itself that way. The other aspect of this is the use of the enclosure protecting the wood structure during construction. Okay, so if we look at a typical sort of build sequence here, what we're finding even with the mass timber, so here's a bit as we go up. So as you just noticed and sort of popped in there, as the building's going up, this black here represents this would be potentially a waterproof floor. So you'd actually make a waterproof floor every 4 to 6 stories, so that you can start your gypsum and other moisture sensitive material encapsulation beneath. So if you have to put gypsum drywall underneath the floors to get your fire protection, you're going to have to waterproof that floor. And so this will sort of build 4 stories, make it waterproof, 4 stories waterproof. And actually when you look at the encapsulated mass timber requirements in the new BCBC and the adoption of encapsulated mass timber requirements, you essentially have to you know, do something at every, if you're going to encapsulate, you have to do something to keep the building dry below that stage. I mean, you can try to install those materials when water's pouring through, but it's just not a great idea. So the way that the code is set up, it actually, without saying it, it almost pretty much says you have to use prefabricated enclosures to be able to build these buildings. It doesn't say it, but if you follow through the understanding of how these are built, you kind of have to. And so we have this type of building that's going to be built all across Canada and BC and in the US. And the only way to practically build it is going to be with prefabrication. So what kind of facade systems might we see on mass timber buildings? You know, when we talk about mass timber, most people think, well, the facade, the walls should be mass timber as well. That, you know, usually is the first place that most people go, and it certainly can be. You can look at load-bearing systems. You know, typically you want to keep your wood out of the load-bearing path here. So this might be a non-load-bearing application. So typically your structure, you want to have continuous columns, especially in taller buildings. You don't really want your floor slabs, which has, you know, shrinkable wood in there, impacting the height of the building and movement of the building. So you tend to remove that from your load path. But, you know, most people's thought process sort of starts here. You could use infill wood studs. You know, if you don't necessarily need wood for structure, you can use light wood framing. This is a bit more challenging with fire protection. So we typically don't see stick framing in mass timber. But we will see, and we have seen a lot of steel stud framing, right? So steel stud framed walls for fire reasons are being used. And then to meet energy requirements with exterior insulation, get some sort of non-conductive cladding attachment or low conductivity cladding attachment, and your rain screen cladding. Steel studs can, you know, be, you know, site built. They can also be prefabricated. So we've seen a number of projects with prefabricated, or at least partially prefabricated steel stud systems that might hang off the slab edge rather than bear on it. And that simplifies the prep and the installation there. We've considered precast concrete and lightweight precast concrete sandwich panels for mass timber buildings. This can be done. There's no reason you can't hang concrete facades off of wood buildings. It's sort of counter to the carbon discussion, but if, you know, that's what the desire is for that enclosure, then that can be done too. A lot of curtain wall systems, some window wall systems, but you know, a lot of, you know, glazing here. The challenge with, you know, conventional curtain wall is the thermal performance isn't meeting the targets on a lot of these jobs that we're looking at. So we're looking for better and better systems. We're running, you know, fewer and fewer options as a result. And then where we'll talk a bit more later on is actually building hung mass timber systems like curtain wall, so like non-load bearing mass timber systems, and then connected either like precast or curtain wall or some other sort of joint connection system. So the idea is that you can use thinner amounts of mass timber and then hang it, you know, basically thick sheets of plywood or thin cross-laminated timber, and that's your facade system. And I'll explain more what I mean there in a bit. And as we build these facade systems potentially out of wood, you know, you've got the load-bearing application, and typically what we try to avoid. We've got systems where the, you know, platform framed here, or sorry, balloon framed is platform framed here on the left, and we got balloon framed here. That's one way. That's the challenge with balloon framing is that, you know, you have a lot of joints as you go up, and it's harder to, you know, prefabricate the whole piece. But we see a lot of taller wood building, especially in Quebec, actually sort of built this way. And then where we're looking now is where we don't need that exterior structural load-bearing wall. And actually, we can go from like something that requires a 2-hour fire rating to down to something where it only requires a 1-hour fire rating and can be lighter, and then hung, and then cheaper actually, and from a wood standpoint, are hung systems. Okay, so you can have bearing, non-load bearing, and then of course the considerations facade engineers for movement. So I'm going to quickly go through a case study because most people have heard of this study, this project by now, but I'm going to cover it anyways. Just some of the key aspects that the industry learned from this project. So Brock Commons, UBC, tall wood house, and the facade design there, and what drove that. So that project, for most people to know, it's a mass timber building. It's 18 stories. University of British Columbia. It was built 4 or 5 years ago now. And you know, as facade engineers and closure consultants on this project, you know, this was sort of the palette we had to work with there. And we also had a, you know, nice wood structure, concrete topping, drywall on the underside for encapsulation, fire protection, and then encapsulation around the columns there. So this was designed by Acton and Urban One was the construction manager on the project. And when you look at the design criteria that the team and we had to meet, we had, you know, first was set out by the owner was, you know, we need fast installation. So right away, looking at this building in the early meetings, it was like, all right, we need something fast, and we'd like to shoot for 1 floor per day and watertight to protect that structure. Okay, so we need to protect the wood, and the structure is going to go there together quickly, so we need the enclosure to go together quickly. This particular job, there was no desire for scaffolding, both in budgets and also access. And so no access to the exterior, and also no desire to go on the outside with swing stages for sealing or finishing. So do it all from the inside, or do it all from as it's going up. Be resistant to water and able to install in the rain. Pre-installed cladding and windows, so factory installed windows. Durable and high performance, of course. Thermally efficient. You know, the initial design was targeting passive house. It wasn't built as a passive house in the end, but the idea was that the wall system there could be for a passive house building if it was desired. And then as the actual design ended up being for ASHRAE for code minimum, but still pretty efficient there as well. And at the time, the budget for window wall in Vancouver was around $50 a square foot. And other competing systems, you know, stick built would have been $50 a square foot installed and finished. And so this facade system had to equal or less than that, and to be able to be viable. And so when you look at the options available at the time, and even in the industry, it sort of went through these two thought processes. You can either prefabricate this as small panels with separate windows. And if you look at some of the other university buildings, Orchard Commons and others at the time, they were like this. They were sandwich panel, precast concrete with window wall strips. And that was looked at here. And interestingly, that, you know, when the modeling and looking at through this was actually going to be too slow. It was going to slow down construction, and there was too much site prep and slab prep. And so very early on, the team decided that we were going to go down the road of a large panel with pre-installed windows. So in the end, the same or very similar window to wall ratio with larger panels that would have been lifted by the site crane that would be, you know, 20 to 35 feet and 1 floor tall, and the windows would be installed ahead of time. So to get all those criteria. So what was really innovative about this project is we were actually able to build, there was a bit of a competition that was done to build this wall system out of wood, a wood backup, steel frame backup, and then concrete. So lightweight concrete sandwich panel. And so we actually had 3 teams build the wood option, steel stud option, and a couple options for this one here at the end, but then also the concrete option. So we actually got to try out on a structural mock-up that was actually built for the building 3 systems. Okay, so these are, you know, proving out that this could be done on this scale and how it would work. In the end, the winner for this particular competition was Centura with their steel framed system. The concept worked quite well. It was demonstrated, it was fast, it was on budget, which was important with the initial metal cladding, and a proven company and bonding. And, you know, when you look even at the other offerings, the teams there, I mean, the concrete team had been around, but the wood team hadn't done something like this before. And so it was a little early, I'd say, for the wood industry to be able to jump on a project to this scale. And so we've been sort of building, you know, in parallel after this project with the wood industry to bring this forward. Interestingly, the concrete option at the time, so $50 a square foot was hit, and then the sandwich panel was about 5% higher, and the wood option was about 10% higher at the time. So all were viable, and they're all within, you know, reasonableness for cost as well. So how does this work? You know, and many people have now seen the details of this, but it's a steel stud frame, light gauge steel frame, cold form steel with HSS components, some HSS framing in there as well, but essentially a steel frame with all the steel in there and anchors. There's not a lot of thermal performance left, so you tend to shift the insulation to the outside And then you can get different clips at different depths to get whatever thickness of insulation you want, up to like a foot nowadays. The gypsum was covered in liquid applied membrane, so we could then bring that into the inside and do a seal on the inside of the returns. And then the cladding, flashings, and the windows were all pre-installed. Okay. So the first test was a performance mock-up. This is a entirely new system. So you do a performance mock-up, and you can see this is a time lapse. So that's basically half an hour for those 4 panels, and they're in, and then they just go around with, in this particular case, sealant, structural silicone sealant on the inside, but it's all done from the outside. And so you can see how fast, and it was, first proof is that, and then you testing, and after the testing, we made some modifications, look at improvements to the windows and other details as well. So I mentioned the windows in the panels here. These are from Phoenix glass from BC as well. So this is a view inside the shop. If you're prefabricating, walls, you typically need to lay them down flat on tables. You need jigs to keep them square. Anyone building windows knows that you need to keep everything nice and square. You can see the space here. This is a leased warehouse space. And this is, you need to sort of, like, if you imagine doing, 24 panels per floor, and you got to do 1 floor per week, you kind of need to do the math to figure out how big a space you need for something like this. So you can see the different, steel stud, gypsum, liquid applied membrane. Everyone's inside, nice and warm. No hard hats needed. It's very, nice working environments. And the great thing too is there's tons of repetition, so the quality conceivably can go up and up and up. The windows were all installed into the panels, and then they were tilted up and then brought to site. So this is a condition on site. On site, there's a steel angle around the building. The anchors are there from the panel below. You've got bolts in the top. So essentially, the structural connection are bolts along the inside, and then there's a connection, vertical connection to connect the panels together. And they're hung. They're hung like curtain wall would be. They're hung like precast panels on the outside of a building would be. So their panels, there's 4 to 6 panels on a truck, and obviously the logistics for, this is what constrains some prefabrication a lot, is like how big a low boy truck can you do, how high can you be, but residential buildings in particular, where something like, 20 to 35 feet or so, or depending on your truck, depending on the height here, and these were 10 feet tall. And so you can easily fit those in there. And you start running into constraints when you go over the tall floor to floor, but then you can look at different panel configurations. So site installation, they're flying them into place. On the inside, this is all you're looking at there, dropped in. The corner panels were prefabricated as one entire unit to simplify the installation there, which worked quite well. And there's always discussions on how you do corners, and that's one of the big things that comes up early on. There's a view from the inside, showing the corner windows, the panels. This particular design of this panel used a silicone sealant joint. So we used the silicone from the wall panel returned to the inside of the building, and then we had gaps between the panels that were furred out actually by wood, and allowed us to do a single component structural silicone joint. And this was designed for elastic and actually inelastic movement of that structure there. And so for wind and movement there, essentially that's designed to flex with that and not shear, not break. And then in a big earthquake, they actually, if this is moving 2 to 3 inches, then you're going to get a bit of damage, but that's expected, but as long as things don't fall off. But actually, we pushed this beyond an inch, and it actually remained air and watertight during the mock-up too. So, that, this is relying on site labor to do a good job here. So a fair amount of QA/QC needs to be done for something like that. Considerations too, if you're doing a sealant joint, you need to get past your slab edge. So there was a big enough gap that could be done and tooled properly. And then you can notice the key thing too is seals, air and water seals, always outboard of structure. Trying to have structure penetrate through those is just a nightmare. Of course, then, just like we do for window and curtain wall systems, you do field testing, commissioning, air leakage testing, water testing to make sure that the windows and also the joints are all, so you're applying, all sealed up. So you're applying 1105 type water testing to whole panels and seals. And we found nothing leaked water. We found an initial couple air leaks, and we actually traced down the air leaks, and it was where the installers had left the shims and the trade doing the sealant. Didn't, you know, they just kind of got lazy and stopped the sealant joint of the shim, not realizing that, you know, well, maybe they're going to come back later, but you know, this had to be taken out. And so once you do a, you know, full QA/QC, you realize, okay, that's you know, you need to remove these and sequencing. So they fixed that and then sealed it up. So and then retested, and of course everything has to pass there. So didn't leak water, did leak a bit of air. That was fixed, and then went along their way and sealed up the rest of the building, and a lot of QA/QC reviews. And so one of the things we've been looking at is like, hey, this is nice, it works, you know, it's durable, it's using silicone, it's going to last the life of the panel here. It's in a warm, dry location. You know, if you had to maintain it, you could, but really this is something that's going to last the life of that building. You know, can we do something better? Can we use something dry seals? Can we use gaskets? And this is where things have been sort of pushing beyond that. So this is our site installation here at pace with the structure, and you can see pretty simple. So next case study is a project in the US, just wrapped up, just got occupancy in COVID, whatever that means nowadays. But this project had a goal for net zero, built with passive house principles for the enclosure and air tightness. This is built by Katera and designed by Michael Green Architecture in Vancouver. And when we got involved early with this project, the concept here was to you know, in the structural system, we've actually got 15-foot floor to floor. And so there was some discussion early on, like, you know, let's try it, but, you know, let's consider the 2-story tall, you know, 12 foot, 10, 12 foot by 30-foot tall panel. And so the early on, the design of this facade in the system got set on this tall vertical panel, which it worked, but it would have been a lot easier if it was horizontal. But you know, good to learn from the you know, some of these earlier projects. But you know, both can work. It's just easier to go to horizontal. So the mass timber structure here, it's all CLT and glulam, and provided by Katera, and actually Structurelam provided a lot of the CLT as well, because Katera's plant wasn't running in time for the schedule of this. But so it's a, you know, Canadian. It's actually all Canadian wood actually in this project in the US. Canadian fiber anyways. So mass timber structure here. So you can see the CLT, the glulam, really nice open space on the inside. Mechanical services running through here. Neat thing about this project is we've got CLT, shear walls and core with steel reinforcing actually, and essentially post-tensioning going up through that steel structure. Essentially rods, actually not much post-tensioning, but essentially rods. So steel wood hybrid to resist the lateral loads in this building. So pushing that technology on this tall 5-story building. The panels here, the facade, the idea, you know, working with Katera and MGA on this was we're going to take mass timber, so CLT, 3-ply, and because these are vertical panels, and they're quite tall, you know, you can actually pick these up here, and you can lift these, sort of tilt them up and lift them into place. They're actually, believe it or not, stiff enough to be able to do that. But the design of this building had terracotta, and it was agreed that lifting terracotta and shipping terracotta around it, which is really just hooked in, it was probably not going to work that well for prefabrication. And these windows are quite large. And another interesting fact is these windows are from BC. Euroline provided their passive house window here for this project. They're huge windows, and there was concern that if this large triple glazed window is laying flat, that there could be some impaction of the glass. So the decision was made to install the windows on site, but prep the rough opening ahead of time. If the windows had been a bit smaller, or potentially some of the cladding was going to be installed, then we would have done it in the factory, but it was decided that it would be done in the field. Could have gone either way. So it's covered with a air water resistant barrier membrane, in the case exterior insulation. A lot of back and forth here. Initially it was mineral wool and clips, and then for structural reasons we ended up going back and forth and ended up with insulated metal panels. So insulated metal panels then sealed up, so they're watertight, so you don't get water getting in behind there. And then the insulated metal panels with the carrier rail system from Kingspan, that's the horizontal rail here, that this would pick up the vertical girts of the cladding. So from a thermal standpoint, it's just screws through the insulation supporting the cladding, which is quite strong. I've done a lot of testing on that lately. And that was so from a structural and thermal standpoint, pretty efficient and, very high R value. These panels themselves are like R50. So there's the panels all going in again, a couple workers working away, getting a number of panels done per day in sort of a setup like this. So not quite large a setup as Centura had, but just sort of working away at the panels. They get stacked up, and you can see they're separated here on done in shims, and then put on the back of a truck. Lifted up with the crane, they just lifted off the truck, dropped into place, anchors were connected. We have a connection anchor in the midpoint and wind anchors at top and bottom to support the panels. And then the windows, some plastic was put in there temporarily, but then the windows were installed shortly thereafter. And they're installed pretty simply because all the prep had been done with the membranes, just brought in and then perimeter seal, screws, and then done. So the windows are going in here. Next step is sealing between the panels. So these particular panels, so they're hung, and again, they're moving independent. So in a seismic event, these panels are drifting with the structure, but they're not supporting the weight of the structure, right? So when you go 30 feet tall, you can just do the calculation for interstory drift on that, and it's like 6 inches at that extreme location here. So we needed a fairly flexible seal here. The silicone sealant joint wasn't going to work, but silicone strips or silicone sheet, which we use a lot in the curtain wall industry, was used. Because we weren't installing cladding and on site, we actually decided to do this from the outside. You could have done it from the inside just as easily as the outside, but it was decided to do from the outside there. And so that was done from the outside, for the verticals and then the horizontals to seal all of that. And of course, this is again site workmanship. So then you're going to do some commissioning. The really neat thing, and actually sort of side benefit that we realized too, is that the fire and smoke seal between the floors was a Hilti silicone, and actually we were able just to spray that through here over the mineral wool, and it actually bonded tenaciously to the silicone strip there. So that provided a nice seal, and we used it for another carpets and other locations as well. So again, air water testing of panels and joints. So air testing, initially found quite a few leaks that related to workmanship and some details that needed to be cleaned up. So we tweaked those. I did water testing, and then a whole program, a QA/QC program, was put together to seal these up. Right. So we, again, sort of like Rock Commons, you're relying on workmanship in less than now on the outside of the building in less than ideal conditions. So what happened is about 100% of the seals were actually QA/QC'd and actually tested in the little device that we came up with Katerra to do that. You can see from the inside construction. On the outside, after the joints are sealed up, there's mineral wool insulation on the outside of the panels to fill in that cavity for the terracotta supports, the terracotta and the cladding going in there. The building near completion. It's really nice curtain wall. Actually, you'll see in this picture here some Okalux glazing there as well. I haven't used that on a project before. It's kind of neat. And there's some exposed CLT on the underside of a very well protected. You can see the terracotta here and the pattern here of this terracotta hanging over. And actually, the upper panel joint here is actually an overhanging joint. So in an earthquake, that upper panel moves independently, separate from the lower panel. They don't touch. And that's why there's no really a big ugly joint there as well. It's the inside. Nice, beautiful windows in here as well. Turned out really well. Nice, very, very successful project there again. And hats off to Katerra and the team for pulling that one off. You can see on the inside too that the vertical joints, they just put wood battens as cover strips. All the air and water ceilings on the outside. This is just a visual seal. As a result of all that work, interestingly, this building, so mass timber, prefabricated, and net zero, is currently the tightest building that we've ever tested in our database in the US. There's some passive house, smaller passive house jobs, but this is definitely the largest project of this scale to be this tight. So it's like 0.034 CFM per square foot at 75. The FIAS target was 0.08, which is quite tight. PHI target was 0.12, and the Washington State target was 0.4. So we're like 12, 13 times tighter than code. So very tight, and that's a result of that design, testing, and then follow through by everyone on the team. So where are we going next is, moving.
So Graham,
just wrapping up here. Yeah. So where are we going next?
Yeah, perfect.
Yeah, this is the end here. So so we've got working on a number of systems using it's fenestration technology. That's the best way we could seal up these panels. And that's so we've been for years now looking at chopping off curtain wall parts and now extruding our own curtain wall parts, chicken heads, and details and anchors to do this all with dry seals and gaskets. Essentially same sort of process. You got mass timber of some sort, covered in a membrane, exterior insulation, cladding, factory installed windows, systems that are going together, like unitized curtain wall, like precast systems to meet the target, very large panels, up to 40 feet long if we wanted to go, but typically in the 20 to 30 foot range. Lots of mock-ups have been done. We've been working on a number of prototypes and examples here to sort of prove this out and show the air and water tightness of these systems. There's a competition where 3 teams from across Canada and the US are actually each developed their own system where it's wood back. It's basically curtain wood, where it's wood and it's connected like curtain wall or precast. Each of the teams has a different connection system, but essentially this is, very quickly becoming real. In this particular case, it's a R40, it's a passive house wall, so it's like somebody would say a ridiculous amount of insulation, but a whole lot of insulation overshadowing the 4-inch backup wood there. But that's sort of the concept. We're seeing this in beyond wood. Our passive house projects that are out of steel and concrete. Again, steel frame backup wall, prefabricated, punched windows, factory installed. Over and over and over again, this keeps coming up. And so the opportunity here, and last slide, is we're going to need prefabricated systems. The mass timber industry is definitely a catalyst leading this, but we were already seeing this with net zero passive house goals. Huge opportunity here. Think beyond the window. This is a big opportunity for window suppliers to produce wall systems, or at least have some say and development here. It's instead of trying to improve spandrel panels, we're going to move beyond spandrel panels and so to real, higher performance. And so there's the real opportunity here. So will it be 2032? Will we be called the Fenestration and Wall Association of BC? I added that in there. But will we be that? We could. Is there a wall industry that has the same support? There isn't right now. So I'd say that I think we want to adopt this and we want to accept this and grow their membership. So with that, we'll take discussion and questions. Thanks, Marie, and thanks, everyone.
Thank you. That was tremendous. Just my own 2 cents worth. We've been working on a little single-family example of all of this stuff, and yeah, modular is the only way that you can get this stuff to happen. We're 45 minutes away from the Okanagan where we are, and they can't find labor down the street, let alone anybody interested in going an hour there and an hour back every day to get to work. So we wanted everything to show up on a truck and basically be bolt on. And it's been an amazing learning experience for us too. So maybe one day we'll share some of that with everybody. In the meantime, we have 3 questions that I would definitely like to get to you here. Navrip Sadhu asked, vinyl windows are used in America, Europe, and in Asia, high-rise applications. We've heard that there are discussions on possibly reclassifying vinyl as a non-combustible material in Canada, and therefore allowing it to be used in high-rise application with less restrictions. Do you know anything about this possible shift? Any quick comments on that? That's a loaded question.
So the fire side has already been addressed. A lot of work, Fenestration BC supported a lot of that work, and a lot of the local suppliers did. But what you'll see, 100% vinyl window wall doesn't solve the problem. And I think that's important to realize that if you just go to vinyl instead of aluminum, that is not the solution to the upper end. It might meet your intermediate steps, but we actually need some walls in these buildings, and that's what we're learning over and over again. And so put that vinyl window and maybe potentially even build the wall system out of vinyl and steel components and sort of rethink it that way. Unless you can get your spandrel panels up to R40, R30, then it's not going to work in some of these upper echelon projects, which are going to become the code minimum in 2032. So I wouldn't invest a lot of money in developing a system. It's not going to be not going to work in 2032.
I'm gonna try. Is Jason available? Is there any way we can get her or his audio clicked on, Zaina? He was gonna ask this question.
Need to unmute myself. Hold on a sec, and I will unmute Jason. Where are you? And then Jason, you just have to unmute yourself.
And while we're doing,
There he is. Okay, Jason, I'm going to unmute you, and then you're unmuted.
Can anybody hear me?
Yes, Jason.
Great, thank you, Graham. My question: there's been lots of great examples of these walls being built and they're being field commissioned, and they seem to be performing pretty well. But before construction, where, for example, Broad Commons have done a mock-up and they've done all your interstories drift testing, all your air and tightness, your thermal cycling, really to ensure that the product is quality. And since then in BC, I have not heard of any intertech testing for any other types of wall panels yet either. So how as a consultant would you be comfortable enough with a different wall assembly with perhaps balconies, different stud spacing, different thermal clips? How will you get comfortable enough with that type of prefab wall being proposed, and in order to allow for it to be used on the job?
Yeah, great question. So we especially anytime you're developing a new facade system, you need to do a performance mock-up, and that should be tested at a lab, ideally in close to where the project's going to be. So, for your case at Coquitlam there, right? And so there, a lot of these systems being developed, they're being tested in other places. I mean, the US one was tested there, but they're coming, and it's slowly coming. We're at the tip of the iceberg here, and there's a competition right now in three systems. The winning team will be coming, and it'll actually go through a full PMU to vet it out prior to use on the particular project that we're looking at here. So now, you don't need to do it out of wood. You can do it out of steel stud too. And any of these new systems, it's all comes down to the joints and the details, and how they handle stress, how they handle the interstory drift, and then the cyclic movement. So it's a must. And so to make sure it's done, you need to write it into project specs. But the facade systems are, they're enough of a risk. So most people hopefully are realizing that they can't just jump into this without some sort of proof of concept and testing. And we're definitely pushing it that way, and I know many others ours as well. So, yeah. PMUs all the way.
All right. Yeah. I'm struggling with a few projects where getting to that level of testing is very costly and time consuming. So it's just good to have another perspective on it.
Yep. Nope. It's invaluable, and it has to be done. So. The window
we're just
company
building a bunch of stuff in our warehouse and hitting it with garden hoses to start. You got to start somewhere, and developing your own ability to test and retest ends up being a fairly powerful weapon too.
I think what we're
so
lucky
to your point, Graham, if this is going to specialize to people looking to build walls that are already glazed and become a little bit of a more whole system supplier, it may be worthwhile developing some capacity to do some preliminary testing to start.
I think we're lucky in BC. Window suppliers already know they need to test, and you're already testing. We're already in a market where that's happening. And so the development of these whole facade systems, I mean, it's a logical step. If someone tried to skip that, I'd be surprised. But
Okay, for in the interest of time, we're 5 minutes over, so I'll ask our final question here for the, well, we got a few here. Let's go quick. Are you finding any challenges with weather and air sealing with panelized wall systems? I think you touched on that well. Any summary comment?
yeah, if you're relying on sealant, it needs to be dry. And that's why we're pushing towards some of these drier seal systems. You know, you could be a dry seal primary and then you might have a backup with a wet seal, but you know, getting those walls on and the roof on baffles, you know, the majority of the rain into these buildings as long as the windows are installed. And then once you're at that point, you know, where is that joint going to be, right? If it's a sealant joint, if it's on the inside, it should be dry at that point. But yeah, not running into too many problems. Cold weather, you got to watch that. So you got to pick the right sealant, or you might have to heat, right? So.
And Dave Goldsmith asks, why are the floors hung from bolts that are in tension rather than held from below? The floors?
Yeah, so ground bearing versus hung, either can work. There's both. We've seen both, and we've seen both concepts. For it just becomes an installation question. You know, ground bearing panels versus a top hung panel. Both can work in the design of both of those. You know, that's why we have facade engineers to look at these pieces. But either can work. Actually, in this competition, we have
and
two.
From Chris Lambert, any data?
One bearing. Yeah. Anyone? Sorry.
So from Chris Lambert, any data on as to how much a slab will shrink over time? And is the slab pulling back, or does it shrink in both lateral and vertical direction? Which is more? I have a bit of a comment on that too, but go ahead.
It depends what your slab is, but typically it's let's say a CLT, and then you might have a perimeter beam near it. The CLT itself, if it's not, you know, it's you know, the movement direction it's expanding, contracting if it gets really wet. But typically, you know, even if it does get wet, it's usually just the surface and a bit of the edge. But yeah, there is potential shrinkage in the thickness of that, and that's where you design your connections for that. Often the time when we're looking at it, you may have a connector on a beam on the face there. And then of course with connecting, you got to watch, you know, can you go into the end grain of the CLT? You're not going to have a lot of strength, you're going to the top. So there's where you connect it into the wood. It's definitely a consideration for curtain wall in particular on these buildings.
Yeah, we were a little bit surprised to learn that there was a sealant applied to all of our GLT panels that we used.
Mm-hmm.
And that created some adhesion problems for some foam assumptions that we had. We were able to resolve it, obviously, but just something to be aware. But the other thing too to keep in mind is these panels come on trucks, so they're typically about 6 feet wide. They may be 40 plus feet long, but they're 6 feet wide, and so there's a lot of control joints along the width of your slab, right?
Yeah, yours was GLT.
So we had to make choices as to what we wanted as our baseline. Yeah.
Mm-hmm. Yeah. So
anyway,
blue
something
blue guide for moisture. If you want more curious about moisture management, that's sort of tied into the blue guide, and you can go to our website and download those there. So, Nuri, I'd love to hear about your project.
Okay, and
example of how to do this in low rise next. So, put your name forward for January.
Yeah. Yeah, we want to get it a little further than it is right now, but I'm looking at it kind of going, yeah, it would be pretty interesting to look at it with its snow all over it today. What was the linear transmittance value of the CLT backup with the large joints to accommodate interstory drift?
So the insulation is all on the outside of all your structure there. And so, and the insulation, maybe not shown on the drawings there, but the insulation runs tight over the joints. So you're packing in insulation all the joints. So you actually have continuous insulation over all your structure. And so you're using different densities of mineral wool in many cases to fill those spaces. So you don't really have much loss at those connections. So it's where your insulation is in those. Now, there's a bit of extra loss around some of the aluminum, but if you got R40 in front of that minor amount of R value in the backup, it's pretty negligible. So the bigger challenge is, you know, knife plates and other supports or balconies, which you need to pay attention to. And you know, that's where we're looking at right now for some projects. So.
And our final question from Jason, on Brock Commons, why did liquid applied membrane used instead of peel and stick or mechanically fastened?
It was used for compatibility. So we knew we needed a silicone joint for durability and movement. And so we needed adhesion, or good adhesion to the substrate, and silicone sticks really well to silicone, and not really the facers of a lot of peel and sticks. And also when you're looking at the three-dimensional corners of those panels, we actually wrapped the membrane around the 5 sides, and it's reinforced around the corners. But peel and stick, as you know, folding over corners creates a lot of origami, little gaps. So it would have been all sealant there anyways. So it was for, and also we could do it indoors. So you could apply that sealant indoors, a lot better than, monolithically better than a peel and stick in those cases. So you can do both. We used the vapor shield on the other project there too. So it's just those cases we had to use a special silicone for that. So. Well, thanks. Happy to take any other questions by email. And
I thank you. All right. I'd like to, on behalf of VenDC and all the attendees today, thank you very much, Graham. As always, fun to listen to you guys playing on the edge, brave enough, bold enough, crazy enough. But I continue to wish you all the best of luck on everything moving in the future, and maybe we'll throw our hat in the ring and take a look at this single family example of it. It's pretty exciting stuff too.
Mm-hmm. Good. Thanks, everyone. Thanks for the questions, and
thank you.
See you in person again someday.
I know.